The 10-turn potentiometer in my ProSystel PST71D rotator no longer functions. Big surprise there. So my rotator controller doesn't work, and I can't tell which way my antennas are pointing because I can't see the tower from my station. The rotator weighs about 75 pounds, and I didn't want to drag it down off the tower just to replace the potentiometer. And I wanted an indicator that didn't require a mechanical connection between the mast and the sensor. I can easily turn the rotator using a power supply and an inexpensive PWM controller, but I still needed some kind of azimuth indicator. A few weeks ago, I made a video of one approach that involved 18 discrete Hall effect switches, and that works, but it doesn't have any better than about 10 or 15 degree accuracy. A very nice Hungarian ham, Csaba, HA3LN, saw my video and told me about a rotary Hall effect angle sensor that is used pretty much the same as a normal potentiometer, except that it continuously turns with no dead spots. Internally, it uses a rotating magnet and two linear Hall effect sensors positioned at right angles, feeding an integrated circuit to calculate the angle and produce a voltage between 0 and 5 volts that linearly corresponds to the angle between 0 and 360 degrees. It has 1 degree resolution and the same linearity, only needs 3 wires between the tower and the shack, and costs about $20 on eBay. So I bought a couple of them and came up with this approach using magnetically coupled wheels, essentially non-contact gears, to drive the rotary angle sensor. I used an Arduino to convert the voltage signal to degrees, filter any jitter, and display the result on a small OLED display. The orange box you see is the indicator for inside the shack and holds just the Arduino and the OLED display. All of the other functioning components you see in this video were 3D printed using white PETG, which hopefully won't get too hot out in the southern Arizona sun. The drive wheel that mounts to the mast is split and simply gets clamped to the 2-inch mast. The driven wheel that connects to the rotary Hall effect angle sensor has a couple of brass shaft inserts to center it inside the housing. There is a small 6mm bearing at the bottom of the housing to secure the shaft, and the cup that holds the rotary sensor both centers it and prevents it from popping up once the lid is on. Both wheels have slots for the magnets, and I chose thin magnets with a lot of surface area to get the most linkage strength. The poles of the magnets for both wheels alternate, so it is necessary to use an even number of them. I used 34 magnets on each wheel, and the wheels are of equal diameter. I left the cover plate off one of the split halves so you can see the magnets, but they look the same on both wheels all the way around. The split drive wheel is of course positioned by the mast, and the housing for the driven wheel has 3 feet with magnets at the bottom to hold it in place on the intermediate plate on my tower. That's the one that is between the rotator plate and the top plate, and which is normally used just to keep the mast vertical when it is out of the rotator. In this video, I have simulated the mast with this hollow black cylinder, and I used a couple of magnets in the base of it to hold it in place on this steel plate for the simulation. Up on the tower, the 3 wires will come out through a hole in the side of the housing and hold the cup and rotary sensor in place, but for this video I'm using a plastic clip to keep it from rotating. So I'll connect up the Arduino now. Once I get that done, you can see that the azimuth indication is pretty smooth, although there is a little bit of lurch, I'll call it that, in the magnetic connection between the 2 wheels as you turn the drive wheel. And the anti-jitter code in the Arduino has a very slight bit of settling time. But once it's settled, it's very, very stable. The Arduino code is extremely simple, literally just a few lines that do the job. And since the Arduino and display would be inside the shack, the code can be modified at any time, even on the fly. That allowed me to include a variable in the code that can very easily be changed to adjust the displayed angle if the magnetic wheels should slip for any reason. If, for example, the display should read 75 degrees while the antenna is pointed at 50 degrees, changing that variable to -25 from my computer via the USB port would correct the display. And of course that could be done more than once if it was needed. However, the magnets I used are 30 millimeters long, 5 millimeters wide, and 3 millimeters thick, and they provide a very strong linkage, so I don't anticipate that being needed very often. It does, however, mean that I can just plop the components in place on the tower and then do a first time setup from the shack. I don't need to align anything in advance. It would also be possible to use the same Arduino to drive a PWM motor controller so that a heading could be entered, displayed on a second OLED display, and then have the Arduino automatically send the rotator to that heading. That code can be added later if I want, and I might do that someday, but for now this scheme gives me the basics of what I need. All of this is very inexpensive, relatively speaking. Knockoff Arduinos can be had for about $10. The OLED display is about $3, rotary sensor about $20. The shaft inserts and bearings are literally cents. And if you were to use some smaller magnets than I used, you could get 60 of them for about 10 bucks. I estimate that it maybe took $5 worth of filament to print the wheels and the housing. Well, I hope you found the video interesting, and thanks for watching. My very strong thanks to Chaba, HA3LLN, for the suggestion to use the rotary Hall effect sensor, and also to my son Scott for the very effective adaptive filter code that he gave me. So take care and bye.